Now we will see the Einstein's coefficients. In the last class, we have seen that three processes. One is induced absorption and spontaneous emission, stimulated emission. So now we will see the coefficients with respect to all those things. The first one is induced absorption. Here we will take the N1 and N2. So N1 is number of atoms in the energy state E1. N2 is number of atoms in the energy state E2. That means if I have we know that, so this is these are the two energy states. One is E1 and another is E2. Okay, what is induced absorption? So we have here the electrons. So these are the electrons. Or if I consider the material, and then we have to consider these all things are atoms. Okay, these all things are atoms. If I consider the bulk material, okay, if it is material, or we have to consider these are electrons if I consider an atom. Okay, so we know that from matter, okay, atoms consists, okay, then atom consists of electrons. Okay, that's why if I consider the matter, then these are the atoms. If I consider atom as a whole, then these are the electrons which we have to consider. So there is a small difference between these things. Okay, now we can consider the matter or the material. If I consider this energy level as a material's energy level, then these are the N1 are the number of atoms. Okay, then it is absorbing energy, that is h nu it is absorbing. If it is only single ray, then it is a photon. Then this is h nu is a energy which is hitting to these atoms, and these are going to the higher states. One by one it will go to the higher energy level. Okay, this is ground state and this is exact state. This we have seen in the last class. Now instead of this taking h nu, if it is bunch of energy is going, then we call it as energy density. This is h nu is the energy density. That means, so h nu is the energy density. Okay, so single photon is h nu, u nu is the energy density which is supplied to the system. Okay, when we supply h nu, then more and more these atoms will go to the higher state, right, and sit here. So like this will sit. So N1 is the atoms, number of atoms in the ground state with the E2 as energy with it, and then N2 are the number of atoms in the energy state E2, that means in the excited state. So this is this process, induced absorption process, which depends on what all things that we have to see. Okay, that means the rate of absorption, the rate of absorption, okay, is depends on what? So how this rate is going to vary? Rate of absorption is proportional to the number of atoms at E1 level. Okay, that means if there are more number of atoms here, then the absorption is going to more and more. Okay, the energy is going to consume more and more if there are more number of atoms in this E1 level, that means ground state level. Okay, again this rate of absorption is proportional to the energy density. Okay, it is proportional to the energy density. that means u nu, right? So rate of absorption is proportional to the how many numbers of atoms are there in E1 level. Okay, in E1 level, that is N1 atoms are there, and this rate of absorption is also proportional to the energy density of the this one, which how much we are supplying to the system. That we can write it as so this is rate of absorption. Okay, the rate of absorption is proportional to n1. Okay, n1 is number of atoms in the ground state, and then u nu. Fine. Next, we can replace this proportionality constant with the constant b12 n1 u nu. Okay, so why we have taken this b12? Because the transition is taking place from the state 1 to the state 2. That's why we have taken it as b1 b12. n1 is the number of atoms. So here we can call this n1 or n2 as a population. Okay, this number of atoms are also called as population of that state. It is also called as population of that state. That means what? The population of E1 state is N1, population of E2 state is N2. Now similarly, the spontaneous emission case. Here we have to find out the rate of spontaneous emission. Okay, what is the spontaneous emission? The spontaneous emission is it has absorbed the energy now it has to emit. So it has absorbed means, so we have these two states. Okay, now the atoms are in the higher energy level here, that is in the E2 state. So it has to come down spontaneously and it has to emit the radiation. Okay, that means this is called as spontaneous emission. So here rate of spontaneous emission is proportional to what? It depends on the number of atoms over here. That means population of N2. It only depends on population of N2 because we are not supplying any energy to this, so that it is voluntarily it is coming from E2 state to E1 state, excited state to ground state it is coming, so that this rate of spontaneous emission is proportional to the number of atoms in excited state, okay, or the E2 state. That means what? This rate is proportional to N2. Okay, so here we can replace this proportionality constant with A21 N2. Why it is A21? Because this transition is taking place from the excited state E2 state to E1 state. That's why in the proportionality constant we have taken this coefficient as E21 and N2 is the rate of number of atoms. So this is rate of spontaneous emission case. So here we have this proportionality constant is called as Einstein's spontaneous emission coefficient, and this proportionality constant B12 is called as Einstein's absorption coefficient. Now next one is stimulated emission case. Okay, so now what the rate of stimulated emission depends on what? Let us see, these are the energy levels. Okay, so atoms are in the higher energy level. Okay, that means in the E2 level, excited state. Now all the atoms are excited by taking the energy. Okay, so now what is the stimulated emission? So it has to emit by extra energy. Okay, so here we are supplying this h nu, right? This is single ray. So if I take a density in the bunch, in the bulk, that means it is u nu. U nu is what? It is the energy density. We are supplying this energy density, so this will stimulate these all excited state atoms, and these atoms one by one will start coming back to the ground state by emitting the photon. So this is stimulated emission. That means rate of stimulated emission depends on the number of atoms in the higher state, that means population of excited state. Okay, that means rate of stimulated emission depends on number of atoms in excited state. Okay, that is into, and this also depends, if I supply more energy and then more and more atoms are going to come to the ground state, that means energy density u nu. Okay, if I write this, then this is proportional to n2 and u nu, right? If I replace this proportionality constant, that means rate of stimulated emission will become, the rate of stimulation will become it is b to 1 n2 u nu. Why it is b to 1? B to 1 because the transition is taking place from second level to the first level. N2 is the population of excited state, u nu is the energy density, where this quantity is called as, that is b to 1 is called as, it is Einstein's stimulated emission coefficient. Now we will find the energy density equation in terms of Einstein's coefficients. Already we have found 3 Einstein's coefficients, that is in case of absorption and in case of the emissions. So that means we have the rate of absorption. Okay, we found coefficient in this case. Okay, and second one is the rate of spontaneous emission, right? This is the second one which we have learned. Third one is, it is rate of stimulated emission. So these 3 coefficients we found, and we have used some equations for that. Okay, so the system is absorbing once, it is absorbing one time, and then it is emitting in 2 ways, right? One way is spontaneous emission, where the atoms are coming down to ground state voluntarily, and in case of rate of stimulated emission case, the atoms are using extra energy and coming down to the ground state, emitting 2 photons. Okay, what it means is, what it is absorbing, that is equal to, it is emitting in 2 ways, right? That means this plus this way. Understanding? So this is rate of absorption is equal to rate of spontaneous emission plus rate of stimulated emission. Okay, this is happening in under the thermal equilibrium. Okay, this is under thermal equilibrium. Okay, that means what? There is an equilibrium between the environment and the system, or you can say some kind of a constant temperature in the environment and in the system of the laser. Okay, so now what is the equation for this? The equation for this, we know that it depends on the number of atoms, that means population in the ground state, and what we are supplying, that is u nu is the energy density which we are supplying, and the proportionality constant we have replaced with the proportionality, that is B12. This is the Einstein's coefficient. So this is equal to rate of spontaneous emission, that is nothing but this depends on, that rate of spontaneous emission depends on the population in the higher state, that means number of atoms in the higher state, excited state, and here it depends only on N2, and the coefficient is A21. So this is because it is from state 2 to state 1, plus this rate of stimulated emission, that is it depends on the population of the excited state, higher state, and we are supplying here the energy density, and the proportionality constant is B21. Again it is from 2 state to 1 state. Okay, so what is the title or what is the aim of this derivation? To find out the energy density. So in this equation, let us call this equation number 1. In the equation number 1, where is the energy density term? It is over here and it is over here. Let us take these energy terms in the left hand side. That means this is B12 N1 U nu, okay, minus B21 N2 U nu, that is equal to A21 N2, right? So this will become like this. So we want the energy term, so we will take this common, U nu into bracket B12 N1 minus B21 N2 is equal to A21 N2. I want this U nu term, I want this U nu term, so that U nu is equal to so that will become A21 N2 divided by, that divides by B12 N1 minus B21 N2. Okay, so here we have to make a small modification. That modification is, here we will multiply and divide by B21 N2 in the denominator of this equation. That means this is U nu A21 N2, that divides by, it is B21 N2 divided by B21 N2 into bracket, it is B12 N2 minus B21 N2. This will remain as it is. Okay, then this is A21 N2 divided by B21 N2. Let us take this inside. That means B12 N1 B21 N2 minus B21 N2 divided by B21 N2. So these two will get cancelled, and this N and N will cancel. This U nu, energy density, that will be A21 divided by B21. Okay, then this divided by, it is B12 N1 divided by B21 N2 minus 1. So let me call this equation number 2. Okay, so here we have a relation to replace the thing, that is by Boltzmann law. By Boltzmann law, we have N2 divided by N1, population of higher state divided by population of lower state is equal to e to the power minus h nu divided by kt. Okay, so these terms have usual names. This is Planck's constant, this is frequency, this is Boltzmann constant, this is temperature. Okay, so we have N2 divided by N1. This is the ratio. This ratio we will learn in the next class. What is this ratio, meaning of this ratio. And now this is the h nu divided by kt. So we have to substitute for this. We have in this equation N1 divided by N2, but the Boltzmann equation is N2 divided by N1. So we have to modify this. So let us make it inverse. N1 divided by N2 is equal to, so that this will be inverse minus h nu divided by kt, that we can in turn write it as e to the power h nu divided by kt. Okay, I can take that in the numerator by changing the sign. That means this N1 divided by N2 is equal to this much. Okay, now this equation 2 will become like this. Equation 2 will be it is u nu is equal to, it is A21 divided by B21 1 over, so this is ratio B12 divided by B21, then this is e to the power h nu divided by kt minus 1. Right, so this is the equation, and I'll call this equation number 3. Equation number 3, we have to compare this with the Planck's law. So already Planck has found the equation for energy density according to Planck's law. He already has found that we have this. He has the energy density equation as 8 pi h nu cube divided by c cube. Okay, and we have this 1 over same thing, e to the power h nu divided by kt minus 1. Okay, let us call this equation number 4. Right, we have to compare these two equations, equation number 3 which we have found till now, which we have derived till now, and equation number 4, that is Planck's law. I have taken this directly to compare these two equations and find out what are the values of this coefficient and final equation for this. Right, so now let us compare. Okay, by comparing these two equations, so we have some constant quantity here also we have some constant quantity, and here in this case this is 1 over some denominator term, this also 1 over some denominator term. In this case e to the power h nu divided by kt is there, here also e to the power h nu divided by kt is there. There is a similarity between these two equations, so that we can write it as, so here from this equation, comparing equation 3 and equation 4, we can write it as A21 divided by B21 is equal to, it is 8 pi h nu cube divided by c cube. Fine, so this we can compare and equate that. And next is, here we have e to the power h nu divided by kt minus 1, here also e to the power h nu divided by kt minus 1. So here we don't have anything, means there will be 1 multiplied with this, so we can compare this B12 divided by B21 is equal to 1, so that this we can write it as, it is B12 is equal to B21. What is the meaning of this? This is the absorption coefficient, this is the stimulated emission coefficient. That means the absorption coefficient, or we can say the absorption is equal to, it is stimulated emission coefficient. What it means? Now with this, let us write the final equation. Here we have equated this B12 is equal to B21. That means whatever it is absorbing, that is emitting by stimulated emission. So now we are writing this for the indication purpose. The transition is taking place from one state to two state, and here it is from two state to one state. Okay, when these two are equal, then there is no meaning to write the subscripts, so that we can drop it now. So by dropping the subscripts, okay, of A21 and B21, okay, when we drop this is equal to that, so that this is final equation I can write. Therefore equation 4 I can write it as, that is energy density equation, that is U nu is equal to it is A divided by B. Now it is equation number 3. This is equation number 3, we are interested in that. So equation number 3, that is A divided by B, is that under 1 divided by e to the power h nu divided by kt minus 1, because we have taken this as equal, so that this will be cancelled. So here it is, if you want I can write it as, it is B12 divided by B21, these two will get cancelled, and our final equation will be, it is A divided by B 1 over e to the power h nu divided by kt minus 1 is the final equation, and this is the energy density in terms of Einstein's coefficient.